This last video is electrolysis, and by the end of the video you should be able to identify and explain how electrolytic cells work, compare them to a voltaic cell, and calculate amperage, voltage, length of time, or amount of mass generated during electrolysis. So the question of the video is: the lithium-ion battery in a digital camera is 0.93 amps. How many grams of lithium ions must migrate from the anode to cathode to produce this energy in 1 hour? So we're going to try to figure that out, how many lithium ions are moving. So first, we need to know what an electrolytic cell is. If you want to make a non-spontaneous cell operate, you can apply voltage to send electrons in the opposite direction. NOx red cat still applies, but the electrons may travel from the cathode to the anode, so the charges are reversed, cathode negative and anode positive, and this could be used to revitalize a dead battery. So if on the left side you have a regular battery at 1.1 volts, you can plug it into a power source greater than 1.1 volts to recharge the battery, like your actual outlet. Another way we use electrolytic cells is to plate substances such as silverware. So the inner part of the silverware may be made of like stainless steel, other types of metals, and you can take a chunk of silver metal, put it in a silver solution, and make the silver metal reduce to oxidize to silver ions, lose their electrons, go through the power source, and then accumulate onto, let's see, a spoon, I guess here, and then the silver ions that are in the solution get attracted to the electrons on the spoon and reduce and gain mass on the cathode. So the silver isn't generating as if out of nowhere, it's transferring from the hunk of silver to the solution to the spoon. So that power strip is forcing electrons to travel to the spoon because there's otherwise no reason to go there. The spoon is negative and would attract silver ions because of those electrons, and the silver ions reduce onto the spoon, plating it. Remember that reduction takes place at the cathode, which means that the spoon is cathode and it's negative. That's why the charges are reversed. In this case, electrons are traveling still from the anode to the cathode, and the cathode is still increasing in mass. So really all that changed was the charge. Again, electrolysis can be used for separation of particles, for example, water. Water and other solutions can be electrolyzed, and they break them into their pure elemental states. So, for example, if you put water into this electrolysis chamber, it's set up to a battery. The battery tells you that's electrolysis, it required energy. Notice that more oxygens are being hydrogen is being formed, I don't know why it says oxygen, than the oxygen, and that's because there's 2 H's for every O in water. H plus is being reduced to H2, and that would be the cathode. Notice the cathode is hooked up to the negative battery. And oxide is turning to oxygen, and it's oxidized at the anode, but again, the anode is connected to the positive part of the battery. Salts try to do this too. A brine solution of sodium chloride could be zapped with electricity to separate. However, the diagram shows that hydrogen and chlorine gases evolve, which could be really deadly. Chlorine gases are not good for you. So not the sodium metal, and that's kind of peculiar. Why isn't the sodium doing that? So if you use your reduction tables, waters are better at reducing the sodium. So the water in the solution reduces instead of the sodium. So if you look at these values on your reference table, water only required 0.83 volts, and the sodium required 2.71 volts. And so you're going to choose the particles that are best at reducing. So again, since chlorine is the worst oxidizing than water, however, the solution is basic, so the water will not work out so well. So you have to pick the water example where you see the H plus ion, and you can see that the chlorine produces more voltages than the acidic one. So just because electricity is used to separate salt doesn't mean it actually creates the salt you wanted to separate. The water might get in the way. This could also use to take out impurities from an impure metal. The impure metal is placed at the anode, as you can see in the picture. The anode always oxidizes and becomes ions, so the solution gets this ion solution inside. And then the pure metal cathode is connected on the other side to start to purify the anode. So then the mixtures of metals need to be purified. The mixture can be connected to an anode where oxidation occurs. The element better at reduction will be forced to oxidize by the battery. It will reduce into the pure metal cathode, and thus a separation of the two metals will occur. Reduction at the cathode, and the other ions are still in the solution. So to look at the comparison between our old cells and our new cells, NOx and red cat still true. Electrons still flow from anode to cathode in either cell. Voltaic is spontaneous and it makes electric. Electrolytic is not spontaneous. It does not work normally. It needs electric. You have a salt bridge in voltaic, but in electrolytic there's no salt bridge. They're usually in the same container. The charges are reversed, and the way that energy is moving is reversed. And in voltaic it was chemical to electrical, and electrolytic it's electric to chemical. So since there's a voltage needed to reverse the spontaneous reaction, it takes more voltage than it normally creates. Similarly, to make a non-spontaneous reaction occur, you need a voltage higher than the one calculated by subtracting the anode and the cathode. So anytime that the electrons are flowing through the wire, you have a measurable current, and on your reference table, that's denoted as an I. That's is created to measure it in an amp. So the I is a current. I know it sucks, but we've already used C for a lot of other things, and it's represented in amps. Why we can't use A is beyond me. The Q is a charge in coulombs, and the T is in time in seconds. So 1 mole of electrons creates 96,500 coulombs, or a Faraday. We've seen that constant before. I usually remember the units instead. I say a coulomb equals the amps times the time, or cats. So that's why I have a picture of electrocuted cat here. The coulombs equals the amps times the time in seconds. So for example, how many moles of electrons are transferred when a current of 12 amps is run for 16 hours? If I want to use my CATS rule, I'm going to do my current of 12 times my amperage time in seconds, so 16 times 60 times 60, and that shows me how many coulombs there are. And if they want to know how many grams of copper will be deposited by a passage of 3 amps for 2 hours, I'm going to use the CATS rule again. Amperage times 2 hours times 60 times 60. Oh, I'm sorry, I didn't do the electrons here. So on number 1, I had to divide by 96,500 to get the electrons, because it's Coulomb's law's value, Faraday's constant, that there's always 96,500 coulombs per electron. And then in number 2, we're going to do the same thing. We multiply the amperage times the time in seconds to get the coulombs. We divide by how many coulombs there are, 96,500 per mole, and that's how many moles of electrons. If I want to go a step further and figure out how much copper that is, we have to say that copper would normally become the +2 ion and gain 2 electrons, and therefore if you see 0.2224 moles of electrons, you divide that by the 2 moles of electrons that are in the equation to get 1 copper, and copper normally weighs 63.5 grams per mole, so it would produce 7.11 grams of copper deposited. That copper was normally in some other material. Remember, it's not coming out of nowhere. Another example is 1.26 amps ran for 7.44 hours in sulfuric acid, and we want to calculate the volume of gas that evolved at STP. So first we're going to take our CATS rule and do our amperage times our time in seconds. That comes out to be 33,000 coulombs. We'll divide by Faraday's constant to get 96,500 coulombs per mole, and we get 0.35 moles of electrons. Once you know your electrons, you can run it through the reaction. The anode will be water exchanging and moving its hydrogen apart, so it will lose its electrons and oxidize. The cathode will be the 2 hydrogens then gaining them back to form H2. That's the overall reaction for water, where you have 2 H2O making 2 H and O2 when the electrons cancel, because we have to double the cathode. So once we know that, it shows us that the 0.35 moles of electrons had to be divided by 4, because that's how many electrons were transferred. And that gives us 0.0875 moles of hydrogen. If we wanted to know how many hydrogens that is in liters, we can multiply by the fact that for every reaction there are 2 hydrogens. And if you're at STP, that's 22.4 liters per mole. So total of 3.92 liters. Remember, you can only use 22.4 if you're at STP, which the question says. I think one more example. To coat a penny, 0.1 grams of copper must be deposited as copper ions. If the current is 2 amps, how long would the battery need to operate? So now we're going backwards. We're going to start at the 0.1 grams. We're going to divide by how much copper weighs on the reference table to figure out how many moles of copper that is. For every mole of copper, that's 2 electrons, because it's a +2 charge. And so that means I have 0.00315 moles of electrons. Again, Faraday's constant is really important. That will change us from moles of electrons to coulombs. So if I multiply by 96,500 coulombs for every mole, I get 304 coulombs. Now I can use my CATS rule. 304 coulombs is the amperage times the time. I know my amperage is 2, so I'm just dividing by 2 to get the time. I got 152 seconds. So just under 3 minutes, and I'll have my copper deposited on my penny. Ooh, sorry, just lied. Aluminum can. A standard aluminum soda can contains about 15 grams of aluminum coating. If it's plated for 10 hours, 10 amps, how long would it take? So again, a backwards one. We're going to take those 15 grams, divide by how much molar mass of aluminum we have to get our moles of aluminum. Aluminum makes a +3 charge because it's in group 13, so we have to multiply that by the 3 electrons that are lost for every aluminum. That gives us 1.67 moles of electrons. Just like our last example, we're going to figure out how many coulombs it is by multiplying by Faraday's constant, 96,500 coulombs for every electron. And I got 161,000 coulombs. Now I can use my CATS rule to divide by the amperage and get 16,000 seconds, or 4.5 hours. It's probably why we want to recycle our cans, because you need more amperage and use more, we need more amps and use pure ore from Arizona and Puerto Rico, the amount of energy needed to make a can should make you want to recycle the can instead. So back to the question in the video, how can we solve how much lithium is going through per hour? So we would do the Cat's rule, 0.93 amps times the time in seconds, 3,600 seconds per hour, and then divide by Faraday's constant. Say that there's only one electron lost by every lithium, and every lithium weighs 6.94 grams. So that means that we're transferring 0.241 grams of lithium for every hour you use the battery. At this point, you should be able to compare and contrast electrolytic and voltaic to calculate amperage, voltage, length of time, or the mass generated by electrolysis.